Hey everybody, I'm Jeff Mucklin. I'm with the Nurture Nature Center, and this is Science at Home. And in this week's video, we're going to be covering a topic that is really, truly elemental. We're going to be talking about the elements of the periodic table. So this table includes the 92 elements that are found naturally on the Earth. There are some other elements that aren't included here that are made by human beings. I've been starting an element collection. And so I've got, helium gas here. I've got carbon here. This is element number 6. This is a very important one because this is one of the most important elements for life. In fact, it's so important that the chemistry of life, organic chemistry, is all about the chemistry of carbon. You may have some examples of these elements in your home. Aluminum foil, for example. Copper pennies, but not all copper pennies. Pennies made prior to the 1980s were made of pure copper. After that, they were mixtures of zinc and copper. Iron. This is a piece of iron wire that I forged myself, actually. I had to bend it to fit it in there. Maybe neodymium. This is probably one you have in your home. Very strong magnets are made of neodymium. So those are some of the more common elements that you, again, likely have around your home. Some of these elements, though, are actually quite scarce, and you probably have never seen an example of them. So, for example, here's gallium, element number 31. Gallium is a metal, but unlike most metals, which are solids, or even unlike mercury, which is a liquid at room temperature, gallium is solid at room temperature, around 70 degrees, but if you heat it up to 85 degrees, it liquefies. It looks a lot like mercury, but if I was to cool it down just a little bit more, I heated it up before I started this video, it would solidify. It melts at around the same temperature as milk chocolate. Another element that you probably haven't seen before is tungsten. This is the densest, heaviest one that I have in my collection. There's just a little bit of tungsten in there, but it's surprisingly heavy for such a small amount. Yes, everything around you is made of elements. But elements themselves are made of, atoms themselves are made of even smaller constituent pieces. These are called subatomic particles, and they're what make up atoms. Luckily, there are only 3 of them. These 3 subatomic particles are protons, neutrons, and electrons. The protons and neutrons make up the majority of the mass, the weight of an object. And they exist in the center of every atom, and they make up the nucleus. So the center of every atom is the nucleus, and it's a mix of protons and neutrons. The electron is a far less massive object that has almost no weight compared to the proton and the neutron. And it doesn't exist in the nucleus. Rather, it exists far away from the nucleus in the electron cloud. Now, as it turns out, the number of protons that are in the nucleus of an atom actually determines what element we're talking about. If you have 1 proton in your nucleus, you are hydrogen. 1 proton, that's hydrogen. If you have 2 protons in your nucleus, you're helium. If you have 3 protons in your nucleus, you're lithium, and so on. 6 protons makes up carbon. Gold has 79 protons in its nucleus. And the proton has a positive electrical charge. Atoms themselves have no net charge. And this is because the positive charge of the proton in the nucleus is canceled out by the negative charge of the electron cloud that spins around the nucleus. So to help you visualize this, I have a little model here. Here is my model of the nucleus of a helium atom. We've got 2 protons and 2 neutrons. And it still would be helium, by the way, even if there were 3 neutrons or if there were 4 neutrons. As long as there's 2 protons, it's helium. The number of neutrons in any element can actually vary. So we've got our helium nucleus, right? And we'll put it right here by my helium gas sample. So right there's my helium nucleus. And I've already told you that the electrons are far away from the nucleus. How far? I'm standing 3 feet away. Is that far enough? No, it's not. Maybe 10 feet? No, further. 15 feet? No, further. I'm going to have to go outside because I've actually reached the edge of the building. If I want to get any further, I'm going to have to go down onto Northampton Street. So I'm walking down Northampton Street, and I'm already about a block away from the Nurture Nature Center, but I've got a ways to go because the nucleus of an atom is about 100,000 times smaller than that outer edge where we find the electron. So I'm either going to have to keep walking for a while or I'm going to have to get into my car if I want to get to the edge. So I'm in my car and I'm traveling down Northampton Street, and I've already gone just about a mile, but I'm going to have to keep going for a while because I'm still not at the edge of the atom yet.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, actinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. Yttrium, terbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver.
Well, I've driven 3 miles from the Nurture Nature Center, going straight down Northampton Street, and I actually reached the end of the road. It actually ends right here at this parking lot. And I'm just going to cut across this field here because I'm almost there. I'm almost to the edge of the atom. I'm not going to stop now.
There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, fluorine, and terbium, manganese, and mercury, and molybdenum, magnesium, and dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum.
So I'm now at the end of my journey. I've reached the edge of the helium atom. And I've traveled over 3 miles from downtown Easton where I left the nucleus. It's down at the Nurture Nature Center, and I'm way out here at the Charles Schrin Community Center. And there's really nothing between here and that nucleus back at the Nurture Nature Center. The atom is actually mostly empty space. At this point, I would be next to the electron that belongs to a neighboring nucleus, which would be somewhere out in Bethlehem. Even at this enormous scale, the electrons would still be very tiny. If an atom was 6 miles in diameter, the electrons would be about the size of the period at the end of a sentence. But they're very important. The electrons' behavior determines the interactions between the elements. Their chemical properties are determined by the way these electrons interact with one another. So here's a fun at-home project that you can do. You can make your own model of an atom. Here's the model that I showed you before of the nucleus of a helium atom. You can make your own atom, though. You can make any kind of element you want. Maybe, go through the periodic table and pick a favorite element. I think my favorite element is probably carbon, which is element number 6, which means that I'm going to need 6 of the red balls, which I'm using to represent protons. You can use any color you'd like, but just try to paint your protons and neutrons different colors so you can see the difference between the two, and make sure that you have the right number of protons for whatever element you're going to go with. So I've assembled my nucleus of a carbon atom, and you can see it right here. And there are 6 protons here. And remember that there's the same number of electrons as there are protons around any atom. So I need to add 6 electrons. To represent electrons, I'm just going to use these little pebbles because electrons are so tiny compared to the nucleus of an atom. So there's 6 electrons orbiting around my nucleus of a carbon atom. This is one way you can make your model. But here's an even better way, I think. This carbon atom is 6 inches in diameter. So if I want to make these electrons far enough away to be to the correct scale like we did before, I'm going to have to get back into my car. Over 4.5 miles away from the Nurture Nature Center, which puts me right about here in Louise-Moore Park. I'm near the base of the windmill that's in Louise-Moore Park, and I brought one of the pebbles with me, and I'm going to put it right here at the base of the windmill. It's right there. I hope you enjoyed learning about atoms and elements with me in this video, and I hope to see you next time.